Hi. A lot of what we're going to talk about this week in class, and also the lab that you're going to do, is related to what we call blackbody radiation. This is radiation that's frequently referred to as thermal radiation, and it's a result of the temperature of the object. Now, you have probably, especially recently, come across a device that looks like this. This is a infrared thermometer, and it measures the temperature of things by looking at their thermal output. There is a little laser on this one, but this is just to locate what it is that the sensor is actually pointed at. So if you fire this, you get a reading. So my surface temperature is about 82 degrees Fahrenheit. I'm going to change this over to Celsius, and we'll get a look at that. About 28 Celsius. This is a pretty strong magnet. This is glowing a pretty good orange right now, but it's still magnetic. So it's below 1500. See, not at all magnetic anymore. That means it was over 1500. As it cools down, it'll start to become magnetic again and starts to stick. Nice bright orange, glowing very hot. But of course it radiates that away very quickly because the power radiation goes as T to the fourth, and the room is maybe 1200 Kelvin cooler than the steel is at this point. So it radiates away heat pretty quickly. Hi, so now we're back in the lab, and we're going to be examining spectra. Now this is a picture of a rainbow that I took, and by accident I think it's probably the best picture I ever took, because I took it from a moving car with my phone, and I think it's really kind of a nifty photograph. But we're concerned about the spectra. Newton took spectra using prisms. In modern times you would use a diffraction grating, but the principle is still very much the same. The light passes through, and because of differences in the index of refraction related to different wavelengths, you will get different amounts of bending. So, the equipment for this week's lab is this PhET simulation from the University of Colorado. In order to link to things from a Word document, you hold down the Control key and click to follow the link. And that brings you to the University of Colorado at Boulder PhET page, and shows you the blackbody spectrum simulator that you're going to be using. This is HTML5, and as far as we know, it runs on every device well. If you run into problems with this, let us know, and maybe we can work something out, figure out a solution to the problem. But let us know as soon as you can. When you start the simulator, this is what you will see. There is a control box that turns things on and off. We're going to want to turn on graph values, and we're going to want to turn on intensity values. The graph values give you the height of the curve at a given point and the wavelength of the curve at a given point. The spectral power density is the power at a given wavelength. By default, it will show you the peak of the curve that you're on. So if we move the temperature around, it moves the peak left and right and gives us different readings. The intensity, which I'll turn off and back on here, calculates the area under the curve at that point and tells you the total intensity, which is the power per area. So if you were interested in finding the power radiated by something, you would just have to multiply the intensity by the area, and that would give you the power. The temperature range goes from 200 Kelvin all the way up to 11,000 Kelvin, which is changed by this little slider on the side. This little star here at the top of the page gives you some idea of what color the thing would be glowing. So my little demonstrator early on, where I showed you the bright orange, it's probably around 2000 Kelvin.